Questions about anything? Last time I emphasized this formula that I think the book needed to emphasize a little more. It's a very easy way to calculate residues in certain situations. When we're dealing with functions which are analytic near a point A, and the one in the denominator has a simple 0 at A. And that means that g of A is equal to 0, but it's a 0 of order 1, which means that g prime of A is not equal to 0. That happens a fair amount of time, and I used it to calculate the famous integral last time of 1 over z to the fourth plus 1 along the real line. And so one of those sample calculations turned out to be rather easy when you use that fact. There the function on the top would be 1, and the function in the denominator would be would be z to the fourth plus 1, whose derivative is 4z cubed. And so if you stick an e to the I pi over 4 there, that's a non-zero thing. So sure enough, that's a simple 0 in the denominator. And so that's all there is to that. And here's what the book did. The book did something absolutely correct, but it would lead to rather excruciating algebra. So I must say I disapprove of this particular example. I guess it's illustrative of what you do when you don't have a formula. But the book factored that denominator. It's a fourth degree polynomial, and the roots are easy to determine. Those are the red dots I had, 4 of them. 2 in the upper half plane, 2 in the lower. Let's see, the next one is 5 pi over 4. And the last one in the fourth quadrant is 7 pi over 4. Those are just the points plus or minus 1 over the square root of 2, plus or minus I over the square root of 2. But the polar form makes it convenient to write. And here's what the book did. It factored out, let's say we want to find the residue at e to the I pi over 4. Well, then I factor out that root and realize that what I have left then is analytic near that spot. So there are going to be 3 other roots here. 1, 2, 3. And the thing in the square brackets is analytic near e to the I over pi over 4 and non-zero. And so it has a power series expansion, namely A naught, let me call A equal to e to the I pi over 4. This would be A naught plus A1 times Z minus A plus ... And so when you distribute that first term through, you'd get the residue term staring you in the face. And then the rest would be regular power series. And so I did this calculation before. This is A naught is the residue at A. And this is a regular power series. And so it's the part of the Laurent expansion we don't care about. And this part right here is what I call the principal part. It's at a pole like this, it's the part with that demonstrates that it has a pole. So principal part, the finitely many negative terms. Anyway, that residue you can calculate, and that's the way the book did it. The book, residue at a of 1 over z to the 4th plus 1 is equal to a naught. And a naught is the value of that thing in the square brackets at, so let's see, what is that? It's 1 over, those are the other zeros. So we'd have e to the I minus 3 pi over 4 times z minus e to the I 5 pi over 4. Last one, z minus e to the I 7 pi over 4. Evaluated at z equals e to the I pi over 4. That is a correct, let's see, e to the I pi over 4. That's a correct thing to do, but it's ugly and tedious. So I don't recommend doing it that way. My way is much easier. Questions about that? Well, let's see. That calculation I did, it can be greatly generalized for more types of functions. And so there's a useful theorem. Rather than do that routine I did last time, after you do it a couple times, there's a theorem. Let's suppose p of x and q of x are polynomials. Generally, they would have real coefficients, because these problems are useful when dealing with real integrals. So you could think of them as polynomials with real coefficients. They could have complex coefficients, but this is the case they get used most. And we need the one in the denominator, q, the degree of q to be greater than or equal to the degree of p plus 2. And q has no zeros on the real line. Then these integrals that are often needed, integral from minus infinity to infinity. It's interesting, you couldn't find an antiderivative for this function, but you can find these integrals by using algebra. And all it is 2 pi I times the sum of the residues of p over q of z, complex valued versions, where a ranges all the zeros of q that are in the upper half plane. Where a is equal to the set of z such that q of z equals 0. Let's see. And z is in the upper half plane. So that would be the imaginary part of z is bigger than 0. That's what I call the upper half plane. Okay, and here's the proof is a snap based on the basic estimate for polynomials. So proof, the key is the basic estimate for polynomials, which you remember from the fundamental theorem of algebra. I told you we'd be using that thing later again when we do residue integrals. So let's see. Remember what it said is that there'd be a constant so that the polynomial p grows like z to the degree for big Z. And so the basic estimate was, I'll use a b here, mod z to the degree of p. And that was true when z was outside some circle of radius. I'll call it r sub p. And we have a very similar one. I guess here's what I want to use. I want to use a little a, big A, little b. I'll use the same thing for q. I'll use a big B over here, z to the degree of q. And that would be true when the mod z is bigger than some radius that might be different for the q one. And when we're going to do this, we're going to have p in the numerator and q in the denominator. And so I'm going to want to use the numerator estimate. This is my numerator estimate for the p. And this is my denominator estimate for the q. And so I can when I estimate the integral, I'm going to do the same old thing like I did in calculating the two previous examples. I'll use my favorite contour, the d, in the upper half plane. I have a minus r here and a plus r here. And let's see, I would make the r big enough so that all the zeros, this is the whole entire set of A. So A is inside the D. It's a finite set, so because Q has only finitely many zeros, of course. So I make the R big enough so that picture goes, and I call this I'll call this part of it L for line, and this part, the circular part, C sub R. And the key to the whole thing is to show that the integral around the C sub R goes to 0. And so that key is I estimate the integral around C sub R of P over Q dz. By the way, the f of z in this residue theorem is f of z is P of z over Q of z, of course. That's the complex function I'm doing this to. And we can estimate that by the basic estimate for integrals. That's less than or equal to the max on that circular part of P of z over Q of z times the length of the circle. And now I'll have that, I can use that, I'll use the numerator estimate for P in the because it's in the numerator, and that would give me less than or equal to A times R to the degree of P. The modulus of z would be R on that circle. And the denominator estimate for the Q, that was little b times R, that's greater than or equal to little b times R to the degree of Q. And the length of C sub R is half a circle, so it's pi times R. And let's see, I need those inequalities to be true, so I would need R to be greater than the max of the RP and the RQ. And I claim that goes to 0. Let's see, so what would I get here when I mess around? This would be, let's say I'd get a pi times A over B, and I'd get r to the degree of p plus 1. So I'll have 1, that's the pi r part. That gives me another 1 here. 1 plus the degree of p minus the degree of q. And remember, g of p, that number is greater than or equal to 2. Because the degree of p is at least 2 bigger than the degree of q. So this number in the exponent let's see, it's 1 plus that, so that's greater than or equal to 1. What? Degree of q is big. Oh, you're right. Oh, yeah, what am I saying? That's a negative. I need that. I should have put it in the denominator. Yeah, so here's what I was thinking when I did this and not writing. Let's see, that would be 1 over r to the degree of q minus the degree of p minus 1. And that exponent is greater than or equal to 1. And so this goes to 0 as r goes to infinity. And so when I add up when I use the residue theorem, I would get integral around the line part plus integral around the circular part of my f dz would be 2 pi I times the sum of the residues. Of the f for the a that are in this. And of course this one goes to the integral we want, which I should have called I, and this one goes to 0. So check. So after I write out the residue theorem, then I let r go to infinity. That's how you do it. Question about that? A remark, I could beef this up and make it more general. Remember, the modulus of e to the I s z is less than or equal to 1 in the upper half plane when s is bigger than 0. And it was less than or equal to the 1 in the lower half plane when s is negative. Let's see, this would be true when it's also 0. And so you can get a similar thing. So an example of a theorem you could get is that the integral from minus infinity to infinity of p of x over q of x. Oh, let's see, I want to do Fourier transform. Yeah, so I'll have a p of x over q of x. I'll put an e to the I s x here. That's a Fourier transform kind of thing. And you could calculate that. That would be using exactly the same proof. And those facts I have in green there. That'd be 2 pi I times the sum of the residues of that set A. And this would be residues of e to the I s z, p of z over q of z. And this would work when s is positive, with the same proof, basically. And if you wanted to do for the negative case, well, then you do a d in the lower half plane. So the s less than 0 case, do a d, a contour in the lower half, so the contour would be this one in the lower half plane. And then I'd have an A that's in the lower half plane. So that's clockwise. And get something similar. Except you'll be in the lower half plane and you'll have a minus sign. So you get, you'd get that the integral, because it's a clockwise thing, you get minus 2 pi I, and you get that sum of the same thing. But this, I'd call this A sub minus. This would be the zeros in the lower half plane. Zeros of Q in the lower half plane. Same kind of work. So if you're doing Fourier transform someday, that kind of thing could be useful to you. Gives you a way to calculate that thing with algebra. Question? Yeah.
Maybe this was explained in the previous lecture, but why must you enforce the semicircle to move clockwise or the lower half plane? Like, is there a reason you need to always move in a straight line from minus r to r?
Well, let's see. I want to calculate the integral from minus r to plus r, and so that would otherwise I could make it counterclockwise, then I'd get the integral from plus r to minus r, which then I'd take the minus. So you have to take the minus somewhere. So this is clockwise. Okay, so that's a great example of an application of the residue theorem, especially to Fourier transforms. The next exciting one, these are fun, so I don't mind taking an extra lecture to talk about them. Trig integrals. So I guess I'll illustrate this with an example. Let's call I the integral from 0 to 2. This is an important thing. It's going to be integrals from 0 to 2 pi, which, if you study Fourier series or something like that, is a very common occurrence. So it's important that be a 0 to 2 pi, because I'm going to relate this integral to an integral around the unit circle. I'll take cosine to the 6t dt. You learned a reduction formula to calculate this in freshman calculus. It was kind of tedious. You could do it if they locked you in a room long enough. But now we have a fancy way to do it using the residue theorem. And let me explain how you do that. Notice, we know that cosine of t is equal to e to the it plus e to the minus it over 2. And you see that e to the it and you think, ha, unit circle. I feel like I'm parametrizing the unit circle. And in fact, that's e to the it plus 1 over e to the it. E to the minus it is 1 over e to the it over 2. And if I'm writing, that looks like z plus 1 over z over 2. When z of t is e to the it. So we'll parameterize the unit circle. So I'll have the unit circle parametrized by z of t equals e to the it. And then, of course, z prime of t, let's see, z prime of t is important to note. We've done this before. It's I e to the it. And the dz is I e to the it dt. Okay, so the idea is to turn that integral there into a contour integral in the complex plane. And that's not a hard thing to do. It just takes some cheating a little bit. So let's see, I've got the integral here from 0 to 2 pi of, well, I've got e to the it, let's see, e to the it plus 1 over e to the it divided by 2 to the 6th power. And I want that to look like a contour integral. So the plan is I'm going to have this integral around the unit circle, and this is going to be z plus 1 over z to the 6th. Okay, somehow I've got to get that. Let's see. And what I have there is a dt. I wish I had a dz or something like a dz. So the brilliant idea is to, let's see, what do I wish I had here? I wish I had e to the it. Then I'd have a dz. Well, if I'm going to have that, if I give myself that, something I want, I'd have to also take it away. So I'll multiply by 1 in that form. Okay, and that's a brilliant thing to do because this thing here is my dz. And because it's a unit circle and there's so many relationships going on here, this thing right here is I times z. So when you look at that, you realize, aha, I have 1 over I times z times dz. And now I see I have a residue, a contour integral that I can use the residue theorem to compute. Let's see, there's only one singular spot, namely the z equals 0 spot. And that's going to turn out to be a pole. So my integral that I want is going to be 2 pi I times the residue at 0 of 1 over I times z plus 1 over z over 2 to the 6th. That turns out to be a very simple thing to calculate just using algebra. Let's see. Let me do it. How do you do it? Okay, I have 1 over, I'm going to have z plus 1, z plus z to the minus 1 to the 2 to the 6th. That would be equal to 1 over 2 to the 6th. And then I use the binomial theorem and get z to the 6th plus 6z, I'm doing the Pascal's triangle, z to the 4th plus 15z squared plus 20. This is kind of tedious, but 15 over z squared plus 6 over z to the 4th plus 1 over z to the 6th. Well, I don't see a residue term there. Actually, this is not the function I want. I need to multiply in front by 1 over I times z. And so I multiply by 1 over I times z over here, and then it hits me, my residue term equals, who cares what? Let's see, I'm going to get 1 over 2 to the 6th. let's see, I'm going to get 20 over I times 2 to the 6th divided by Z. Plus who cares what? That middle term is the residue. It's going to spit me out the residue term. And I get my answer here. I is 2 pi I times the residue, which is 20 over I times 2 to the 6th. The i's cancel. You expect that because this has got to be a real thing when we're done. And so that's a way to check your work sometimes. If you're expecting it to be real and it's not, you botch something up. And that's 5 pi over 8. And you cancel out all the 2's. So that's pretty simple. It's just algebra. No calculus. No antiderivatives. Questions about that? Well, you can make a general method out of this. Let's see. If I have an integral, the integral's got to go from 0 to 2 pi, so you can get the contour integral, the unit circle. And let's say I have a rational function of cosine and sine. Then, what do? Let's see, that rational function should have no singularities on the unit circle. So our rational function, it's a rational function of two variables. So z of w, I'm sorry. So R is a rational function. We'll have to think about what could go wrong here. And then what did we do? We'd integrate around C, and then we'd realize, the cosine function is z plus 1 over z over 2. We did that carefully. When we do it for the sine function, we'd get z minus 1 over z over 2i. And then when I do the trick of getting a dz, I have to multiply and divide by I e to the I theta, and that gave me 1 over I times z here, and that's times dz. That's what the dt is. And so if this has no singularities on the unit circle, which often it doesn't, it would have finitely many singularities inside. If that has no singularities on C, then this would be equal to 2 pi I times the sum of the residues. And it'd be the residue of that function on the inside. So sum of the residues of the F, where A is in a finite set, where A are the singularities singular points of the f of z, which is that thing in the inside of f of z equals 1 over I times z times that rational function. Z plus 1 over z over 2, z minus 1 over z over 2I. The singular points of that function inside the unit circle. So I would reduce that integral to calculus, to algebra. Because computing residues is usually algebra. Oh, let's see. Okay. Questions about that method? The next important example, I need to use a complex log function. So integrals involving complex log functions. Do a typical example. This kind of doesn't look like it's going to involve complex log function because it's going to involve a square root. I'm going to calculate the integral from 0 to infinity of 1 over the square root of x times x plus 1 dx. And you might ask, well, why the heck is there going to be a log function in that? Well, the square root in the complex case is an analytic function, but it always depends on how you choose a branch of log. So let's see. Here's the classic plan. I'm going to take a contour. Let's see if I can draw this reasonably well. It's going to look like a Pac-Man thing. Okay, so here's my origin. I'm going to follow a little Pac-Man cut here. Like that. I'll call this outer one C sub big R. And the inner one is going to be a circle. Let's see, I like my, it's got to go this way. So I'll call this minus C sub epsilon. A little circle of radius epsilon there. And then, let's see, that function is going to have a pole at z equals minus 1. So there's going to be a pole right there. And I've got to go counterclockwise, so this is going to go this way here and this way here. I'll call this part top and this part bottom. Well, I'm going to call it minus bottom because it's going the wrong way, kind of. Okay, and I've got to think about what my function is. My function is going to be f of z. It's going to be a complex analytic version of the square root function. Z to the 1/2 times z plus 1. And I'm trying to integrate along the real line from 0 to infinity. So there's the real line. And I'm thinking, how in the heck can I use the residue theorem? I need my function to be analytic inside my simple closed contour. Okay? And so I have to choose the branch of my square root so that real line is my branch cut. So let's define a branch. Z to the 1/2 equals e to the 1/2 log of z. That's how we define analytic versions of the various root functions. We had to choose a branch of log for which it would make sense in the region where we're dealing. And let's see, I want to choose the branch of log where the angle goes from 0 to 2 pi. So that's called log of 0 of z in my notation, where log 0 of z is the natural log of mod z plus I times theta, where the theta is an argument, going from 0 to 2 pi. So notice that when in this picture, the argument's going to be going down to 0 on this side, and it's going to go up to 2 pi on this side. Okay. And I'll call this little angle here alpha. And that it's minus alpha, so I'm going to make it symmetric going the other way. Okay. So now in this context, and let's call this whole curve here gamma. Then the integral around gamma is going to be the residue of my f of z dz. There's only one spot where it has it's a simple pole actually, and it's going to be 2 pi I times the residue at minus 1 of my f of z. And that's an easy thing to calculate because let's see, what is it? I can pull out that 1 over z minus. I can pull out the z. Let me calculate it. Residue at minus 1 of f of z is, let's see, I would have residue at minus 1. I'll pull out the 1 over z plus 1, that's z minus minus 1. And then what I have is 1 over z to the 1/2. Okay, that's my f over g thing. That's a simple 0 on the bottom, and my f is 1 over z to the 1/2, which is a perfectly nice function over by minus 1. So you could use that, or you could just realize I could expand 1 over z to the 1/2 in a power series and get the a naught term is the residue. Anyway, that residue is going to be 1 over minus 1 to the 1/2. And you got to think about what branch you're using there. That is equal, in our branch, that's 1 over the natural log of the modulus of minus 1 plus, let's see, I'm sorry. That's 1 over e, what the heck, it's 1/2 log 0 of minus 1. And so that's equal to 1 over e to the 1/2 natural log of the modulus of minus 1, which is 0, plus I times the angle. And the angle is going from 0 to 2 pi. And on the negative real axis, that's I pi. So it's critical to have this right branch right there. And so that's equal to 1 over e to the I pi over 2. Well, e to the I pi over 2 is I. So that residue is a very easy calculation. Questions about that residue? Okay, let's see. I'm probably going to have to save some of these little steps to next time. What's an easy step? easy part. Don't have to think very hard to show that the integral along the circular parts go to 0. As epsilon goes to 0 and r goes to infinity. Let's see, why is that easy? Let's think about, here's an important fact. Whatever branch you pick, z to the 1/2, the modulus of z to the 1/2 is always going to be the modulus of z to the 1/2. Let's see why that's true. That's true because I would have here z to the 1/2 some branch of log. I don't know what the branch is. E to the 1/2 some branch of log. And that branch of log would always be natural log of mod z plus some angle. So we'd get e to the 1, let's see, when I take that modulus, that's the modulus of e to the 1/2 log mod z times the modulus of e to the I theta over 2. And of course, we're choosing a theta when we make that branch. But whatever we choose, it doesn't matter. That's equal to e to the 1/2 log mod z times 1. That 1 is equal to the modulus of e to the I theta over 2. So that shows us it doesn't depend on the choice of the branch. And of course, this is modulus of z to the 1/2. So check. That checks out. Okay, so the last, here's the plan. I'll finish the plan next time. Let's see, I'm going to let, let's see, then I have to estimate. How would I do this? So let's see, integral around c sub r, for example, of my function. Would be less than or equal to the max on my c sub r. Let's see, I've got the modulus of 1 over z to the 1/2 times z plus 1 times the length. Let's see, the length would be less than or equal to 2 pi r. And this max would be less than or equal to, I get a 1 over r to the 1/2, that's the easy part. But this other piece would be less than, I do a denominator estimate and get that that's less than or equal to 1 over r minus 1 when I do the denominator estimate. So it's important to get that denominator estimate that r be bigger than 1. And that goes to 0 as r goes to infinity. And now I'll let you think about the c sub epsilon. So you, for next time, do the integral around c sub epsilon 1. It's slightly different. For next time.